Well, thank you for the introduction, and also I'd like to thank my previous speakers here because they're basically spot on with the topics to ethical aspects and wearable computers. We're going to talk about, unfortunately, more technical things, less ethical, and less sociological, and more how to implement architectures, technical architectures for IoT devices. So I'm going to first give you an introduction of what IoT actually is, because it's a buzzword, right? And challenges that IoT devices have in data processing infrastructures and how to solve them with effective architectures that you build on-premise or in cloud infrastructures for your company. So, as I mentioned, IoT is a buzzword. It's a concept that's actually quite old. It was basically started in 1982 at Carnegie Mellon University. They built an internet-connected Coke machine. So that was the start, the inception of IoT devices in 1982. The concept of interconnecting devices with sensors and chips was popularized at the end of the 90s, the beginning of the 2000s with technologies such as RFID, Bluetooth, and so on. Nowadays, we're basically in full swing with that technology because we have IPv6, we have internet everywhere, and we want to utilize that technology for different applications. We're expected to have like 50 billion devices by 2020, IoT devices in that category for different applications. Most of the applications are, like, again, the repetitive term, smart. That means smart devices in different areas. The first area is what we've seen in the previous talk, smart wearables, Fitbits, Withings, whatever, devices that are personal. The second area are smart homes, like bulbs, Nest, thermostats, metering, and all that. Smart transportation, like auto-sensing parking meters, interconnected devices that count passengers in public transportation systems, and all that. And then you have one very large area that's smart manufacturing. Factories that use sensors and devices to monitor supply chains, level gauges, whatever, in a manufacturing process. That is one of the larger areas where you see a bigger adoption of devices. And then last but not least, smart environment, specifically because of climate change and pollution, we see a great boost in the deployment of IoT devices and environmental systems to monitor pollution levels in water, air, climate, pressure, whatever. And all those devices, weather radars, for instance, are interconnected, connected to a network, and basically send their data in the system. So, if you look at an IoT device, what is it? What's the common denominator of an IoT device? It's basically two things. It's a network interface to connect it with the outside world. It can be a mobile phone chip for data connections. M2M is another buzzword, that machine-to-machine communication. That's one thing, and the other thing is a computing device, right? Just a small embedded device that either is full of sensors or computes something or has a graphical interface. A smartphone, for instance, with a specific personal application is basically an IoT device because it basically can do a lot of other things like place calls, play games, or browse the internet, but it also basically monitors or senses things. Like an iPhone 6, for instance, has like this health kit application that measures and counts your steps, heart rates, and all that if you connect it with other devices, and that's essentially fits into the definition of an IoT device. But most IoT devices are just small embedded chips that count things, right? Like passengers in a bus, for instance. And like another popular application would be beacons. Like maybe some of you know that when you enter an airport, you get a pop-up with advertising, whatever. So that's another IoT use case. So the challenge of IoT is they can't actually do much on their own. They rely on an underlying data center that basically does the heavy lifting of data processing. So you have to imagine that IoT devices only really make sense when they're basically connected with other IoT devices and have a common point of synchronization, which would be a data center. So each IoT device basically sends a data at some point, which is not deterministic. There's no order to it because it depends on network connections, it depends on local timings, on whatnot, on a lot of factors. So basically data gets sent to one data center at any point in time, at any given time, right? And on the other hand, if you have a bidirectional system, that device will expect an immediate update. It sends in data and it actually expects an update, some feedback from the central data center to display something to a user, like especially if it's an interactive device like a smartphone, right? So data synchronization is essentially data center centric. You can't really do it on an IoT device because of its limited processing capabilities and the problem of synchronization with other devices. So, as I said, time and order is the major challenge for incoming events. So basically, data centers that process IoT device data, device records and events, have to be able to handle unsorted, unordered incoming events. They also must be able to provide instantaneous processing of that data with immediate feedback. This actually forces us to build systems that are capable of continuously processing incoming events and update that data and those records instantaneously and send them back immediately. And that is where big data infrastructures come in. They were made and built for that use case. Big data infrastructures allow horizontal scaling at any kind of magnitude. So it really doesn't matter how many devices you connect. And you're capable, and modern big data infrastructures offer streaming capabilities, and that's basically what we're going to see in the next slides. So the fundamental principle of an architecture, data processing architecture, using big data techniques, is that you basically asynchronously process incoming events, because you can't tell when they're going to arrive, and you don't want to have to wait for a device to send it its data and to send it back before you process anything. So you just accept the stuff and say, okay, it's fine, right? You have to constantly process that data, incoming data, and update continuously what you know about everything that you have processed so far. Exactly. And what you should also do is you have to store that aggregated computed data in somewhere that can basically be delivered instantaneously. So the basic principle is that you basically decouple incoming events from its processing to be able to, at any point in time, deliver in real time the results of your processing to connected devices, regardless of how fast they are in submitting their own data. So what we do to achieve that is that we first handle the asynchronous record and event submission by using message brokering systems. Message brokering systems are designed exactly for that use case. You have a queue, and that queue is basically a receptacle for data. An IoT device produces and sends in its data, so it's called a producer. It's sent into the queue, and multiple processing pipelines consume that data at any given time of their choosing, which is as fast as possible. This decouples the necessity to wait for anyone. You just send it in and you process it as it arrives, and nobody waits for anyone. They just work as fast as they can. Typical broker implementation, just to name a few technologies, would be like Apache Kafka, which is a very popular high throughput system for binary message types, very popular, was developed by LinkedIn. Or like more traditional and queuing systems such as RabbitMQ or ActiveMQ, both Apache projects, with MQTT in mind. MQTT, just as it's on the sideline, it's a technical detail, is a protocol developed for IoT. So the second thing, once you have your message brokers in place, is you would build up a stream processing pipeline system. A stream processing pipeline is designed to continuously consume events from a message broking system, update on the fly everything that we know about it, and store the stuff into a real-time database. So typical implementations would be Storm, Spark, and Flink. Flink is increasingly popular, especially in Berlin. It's maintained here. Spark has a larger adoption rate, especially with Cloudera, MapR, and other Hadoop providers. And Storm was developed at Twitter as a stream-oriented processing pipeline system. So those are basically technologies that are well suited for this use case. And in the end, the process data is sent and stored in a database. How much time do I left? Okay. Oh, sorry, wrong. And essentially, the process data is then stored in that database, and that's where real-time, near real-time delivery happens. So basically, by just having continuous updates of your events in that database, you can actually constantly and always deliver everything that you know up to that point through the database. Typically, you would use a cache or a relation database for some use cases, or key value stores, or other NoSQL databases such as Cassandra or Couchbase or MongoDB. Those are all valid choices that you basically see in such environments. As I mentioned, long-term storage is an optional use case for IoT. So you would basically have a stream processing pipeline that computes continuously what comes in, and at some point that data is not relevant anymore, and you basically delete it after some time. That's the time to live principle. But in some use cases, especially like in the auto industry, or insurances would like to keep hold of long-term data. In that case, you basically create a second pipeline where you just store the raw incoming events in a long-term storage, such as HDFS, that's Hadoop distributed file system, or in large document-oriented NoSQL databases that can basically scale linearly by just adding boxes as you move forward. And that data would then typically be processed in batch, which is a more traditional big data approach towards processing. You basically collect a large data set, which is well defined, and then you basically process it until you're done in a batch manner. And typical choices for batch processing would be MapReduce, which is like the more traditional way to do it, or like Spark and Flink on top of HDFS to process that data. This is basically an overview of a full stack architecture, a so-called Lambda architecture, which combines batch and streaming processing capabilities with a few examples. So you would have IoT devices pushing their events continuously to a message broker. That message broker would have two consumers. One of the consumers is a batch layer with long-term storage, as mentioned before. You would basically copy everything to HDFS, have a batch processing pipeline, such as Spark, as an example. You can use other tools as well, where you basically continuously process long-term data. And a streaming pipeline, also with Spark streaming, that stores the data in a Cassandra database. This is just an example reference architecture for a Lambda stack as applied to IoT devices. The Cassandra database contains the aggregated data sets from your stream processing results or even batch processing results, and that is basically delivered back to the IoT devices that want to display information continuously through a REST interface or sending back messages or whatever. So there are like use case specific approaches, but this is basically a sample architecture, how to solve that problem. So coming back to key learnings, the most important thing about effective streaming-oriented architectures for IoT devices is to decouple event delivery with asynchronous message brokering. A lot of people would initially start with, okay, we'll send the event and just wait until the event gets processed and then send back the results. That's what most people do. That actually doesn't work, at least not at scale, right? So decouple that. The second thing is continuously process incoming events and update everything that you worked with to provide continuous refreshed results. Yeah? And lastly, provide a lightweight query interface for the storage for your devices to expose the results of your aggregation to your devices if they require feedback. So that's basically the key aspects of an effective architecture for IoT, with a few examples. Thank you very much for your time and attention. You're welcome. Thank you.